This video is going to cover the notes for AP Unit 2.5, which is called Exponential Function Context and Data Modeling. So we've got some real world examples in here, data modeling being building the regression for exponential functions. So we start out with literally what's an example of an exponential function. So we know the equation for the exponential function is f of x equals a times b to the x, where b is our base and a would be our initial value. So in this example, b is the ratio of the f of x values. We also know that b is the same as r, because an exponential function can also be geometric. And if you wanted to find the equation when you were given values, you'll first get the b or the r by figuring out what you're multiplying by each time here. So for example, 3 times what is 6, 6 times what is 12, or 6 divided by 3, 12 divided by 6. All of that would tell you that r is 2, which means b is 2. And then you'll take and plug in x and f of x. Now you've got lots of options. You can plug in any of these points. Let's say we grab that first one. So let's say we grab x is 0 and f of x is 3. And we plug it in. The f of x would be 3. The a is our unknown. The b is 2. And my x this time is 0. So if I have the 0 input value, hopefully this makes sense, because 2 becomes 0, that becomes 1. 3 equals a times 1. And that means you have a. So if given the input being 0, you already have a. That's your initial value. Now let's say we didn't have that value and we started with 1, 6. I would say 6 equals a was unknown. 2 is the ratio raised to the first power. So 6 equals 2a, and a would equal 3. So it would work for any of the points you pick along this data chart. So when you're trying to find the equation at the end, it's f of x equals the a, your initial value, or when x is 0, which is 3, the b, which is the ratio, raised to the power of x. So this is how we would find an exponential function without a calculator. Now let's talk about how we would find it using a calculator. So it gives you the table of values for the function, and we're going to use it to find the exponential regression. So just like we did quadratic or cubic or any of those, we're going to enter the data into the calculator, and we're going to run an exponential regression. So I'll show you what it looks like on the handheld, and then we'll do it with the Desmos. Okay, so I've got my graphing utility here. I went to stat, I went to edit, and I typed in my values. So -8, -7, -1 and 2, 30, 40, 158, and 280. I'm now going to go to stat. I'm going to go to calc. And if we scroll down past the ln regression, you're going to see exp for exponential regression. I'm going to hit enter. Remember, we want to store this because it's asking questions based on it. So we're going to go second trace and put the y1 in there, and then we're going to calculate. So from here, I get my f of x equals 186.721 times b 1.251 raised to the x. Now on b, it says use the model to predict the value of f of 2. So I can either graph it, and I could go to my value. We're spinning. And because it's probably so high, right, our initial value is off this graph. If I went to second trace and I went to value and I type in 2.5, you don't even see the graph, but it does give you the y value. 326.596 would be, that's how it's rounded. I don't have to go to the graph though, because I can go alpha trace y1 of 2.5, and I get that same answer. So this is 326.5957, so 596. And then the next question says, according to the model, when will f of x equal 100? So this means it wants you to find out when your y is going to be 100. So I'm going to go back to my graph, and my y2, I'm going to put 100. Now I'm going to go back to my graph. It's going to take a little bit to graph again, and we don't see it, but our y value has to be 100. So I'm going to go to I can either hit zoom, zoom out, or I could go to window, And I can adjust my Y max to at least to be 100. So let's say we just do 110. Hit graph. Now it's going to give me my exponential model. And there's my horizontal line. So second trace, I want to see where these intersect. Hit enter on the first curve, enter on the second curve, and guess. And it brings you to the intersection, which is negative 2.792. Okay, now I'm going to show you how to do the same exponential regression on Desmos, because there is something you need to make sure you pay attention to. So first thing I'm going to do is add in the table. So -8, -7, -1, 2, and then 30, 40, 158, and 280. Hit the little regression symbol on the left and hit exponential regression. Now, if you notice and you compare this to what we just did, you'll notice the numbers are a little bit off for both A and B. So here's where it's super important. You need to hit the little checkbox that says log mode. As soon as you do that, you're running the regression that is the same as your TI-83. Now I'm going to hit the little icon above the equation to copy and paste that into the next line. But I need to delete out the y and put f of x so that I can plug values in. You can also easily manipulate your graph so that you can see this a little bit better on Desmos. So now I want to find f of 2.5. So I'm doing f of 2.5. I get that 326.593. And if I want to find where it would intersect 100, I'm going to do y equals 100. I'm going to enter, and notice it inserts that horizontal line. Zoom in if you want, tap on that coordinate point, and you see the negative 2.792. All right, example 2, table gives the population of a city in millions for the selected years, where t equals 2 represents 2012 and t equals 5 represents 2015. So that means that when I enter the data, this is 2, this is 5, this would be 8, and this would be 11. Use the calculator to find the exponential regression, model the data, and then use the model to predict the population in 2023. During what year did the population reach 1.5 million? All right, so I'm going to type in to Desmos. So 2, 5, 8, 11, 0.081, 0.933, 1.36, and 1.85. And then I'm going to run the regression for exponential. Check the log mode. So y equals 0.626 times 1.101 to the x, or f of x, equals 0.626 times 1.101 to the x. Use the model to predict the population of the city in 2023. So 2023 would be 13 years since the beginning. So I'm going to copy my equation. Change the y to f of x. And find f of 13, sorry. So 2.189. Okay, now it says, what year did the population hit 1.5 million? So I need a new equation. Notice this was already in millions, so I don't have to type in a $1.5 million. I'm just doing 1.5 here. And then I want to zoom until I see where they cross. And I get 9.071. So this means 9 plus a little bit of years. So since time represents the years since 2010, 9 years later would be 2019. Now, because it's more than 2019, because it's 9 plus 0.71, that means it actually entered into the next year, which means the population didn't hit it until the year 2020. So 9 years later would be the year 2019, but anything over that means it's gone beyond that year and now would be the year 2020. Okay, so then used a lot in exponential models is the value of E. E is called the Euler's number, okay? It is an irrational number, meaning just like pi, it never ends and it never repeats. We approximate E to be 2.718, even shorter, 2.72 when you're using this for 2 decimal places. It's called the natural base. So if you remember that from logs, we use it as a natural base, okay? And it's a growth constant. So we use this in place of finding B. We always use E when compounding continuously, meaning if you're trying to find the rate at which or the money in which you're earning on an account or on a credit card, and it wants it compounded continuously, which is more often than daily or weekly or monthly, whatever it is, then you use PERT, if you remember PERT, and PERT uses E, again, natural base, which is Euler's number. So 5 important equations, okay, that you need to make sure you could either use or even write. So the first is really the same equation. It's just one has an increase and one has a decrease. And this is simple interest. So if you have something at a simple interest and it's earning, let's say, 3%, okay, if it's an increase, meaning it's earning 3%, then I would do the initial value times 1 plus the percent increase. But we're going to do it in decimal form. So if I started with $100 and then something's earning 3%, it would be 1 plus 0.03 to the x. And then we would rewrite it as 100 times 1.03 to the x. Notice it has growth. That should make sense because it is an increase. Now let's say something is decreasing. So something's decreasing in value, like your car or your phone or a computer. Then I could say it's depreciating a rate of 3%. Now it's 100 times 1 minus 0.03x. So that's 100 times 0.97x. And that has decay, which should make sense because it's getting smaller. Then there's 2 special ones that are half-life and double life. It means literally what you had at the beginning is half the amount, or is now half the amount, okay? So the initial amount that decreases by half every h amount of time. So your equation is initial amount, half, because that's what's left, raised to the t minus h, where h is the time it takes to get to the half, and t would be the amount of time. So if it says the half-life of a certain bacteria or mineral or something is 10 years, then your h is 10. And then it would say how much is left after 2 years. Now your t is 2. The double life is almost exactly the same thing, except it's how long it takes to double. So this is talking about something that has growth. So a bacteria is growing in a petri dish, and it reaches its double life after 2 weeks. Now you're in terms of weeks. Your age is 2, because that's how long it takes to double. And then let's say it said how much would be left after 4 weeks. Now my 4 is t. So this time, the parentheses are 2. And the last one is something that we use in Algebra 2, and that is continuous at a continuous rate, which is PERT. So P, or A, equals P times e to the RT, where P0 is your initial value, R is your rate of growth in decimal form, so just like before, you'd have to take a percent and move it, and T is the time it's in that account. So T is the time it's in this account for all of these. All right, so example 3 says create the model. A, the value of a car is $68,000. So this is my initial amount. And it increases by 1.75%. 1.75% is, move that decimal twice, 0.0175 in decimal format each year. So this is simple interest. The value, which is C, equals the initial times 1. It's an increase, so plus 0.0175 raised to the T. And I'll take it one step further. 68,000 times 1.0175 raised to the T. And then we would simply say how long, or what's the value of the car after 10 years, and you plug 10 in for T. So this is a car that's like obviously gaining value as the years go, maybe a classic car. All right, B, there's 280 grams of bacteria in the dish. 250, sorry. 250 is your initial amount. The bacteria doubles every 8 years. So the double would be Y equals, because it doesn't give us a variable this time, your initial amount times 2 raised to the T over H. So Y equals, our initial is 250 times 2. T is the one that stays your variable. H is the number of years it takes to double, which would be 8. Example 4. Now we're going to actually work these out. Jake lends $20,000 to his friend. Man, is he a good friend. At an annual interest rate of 5.7%. Oh, that's why he's doing it. It's 5.7%. It's a good amount of money to get back. Compounded annually. So this is simple interest. Use the exponential growth formula and find the amount of money owed by his friend after 6 years. So $20,000 is his initial amount times 1. It's an interest, which means it's earning money. So this is an increase, plus 0.057, move that decimal back 2 places, raised to the T, and T is 6. So we're going to type this in the calculator. You can even type it in just as it is, or you can add that 1 plus the 0.057. 20,000 times 1 plus 0.057, raise it to the 6th power. $27,892.02 is how much his friend is going to have to pay him back. B, Elsa invests $200 compounded continuously. So continuously means PERT. At a rate of 6.5%, which would be 0.065 in decimal form. How much is in the account after 8 years? So P is your initial balance times E to the 0.065 times 8. 200. E is above your LN button by your 4. 0.065 times 8. 336.41. Notice I'm rounding to 2 decimal places because we're talking about money. All right, example 5. The table gives values for the amount of a certain substance in grams on certain days. The data is modeled by an exponential function given by f of t equals 3 times e to the rt, where t is the number of days since day 0. The constant r is defined as the continuous growth rate of this model. Based on the table, what's the value of r? So this time, we're given the day, which is the t. We're given the amount of grams, which is the f of t. And you want to find r. So if I plug in, and let's say I just grab this first set. So f of x is 3 equals 3 times e to the r, which is what we don't know. T is 0. So I end up with 3 equals 3 e to the 0. And I've lost the r, which means I cannot use the initial value to find r. So let's try the other one. 7.425 equals 3 times e to the r times 6. Now this goes back to logs, which we haven't reviewed yet. But if I have an exponent that I need to get to, then the goal would be to solve for its base and then log both sides of the equation or ln both sides of the equation. So because this is an e, I'm going to ln. So it looks like this. Divide both sides by 3. So 7.425 divided by 3 is 2.475. That equals e to the 6r. Now to get to that exponent, I'm going to ln both sides of this equation. So ln of 2.475 equals ln of e cancels to give you the exponent. So this would equal 6r. And then we would divide both sides by 6. So in the calculator, I'm going to do ln 2.475. Close the parentheses or hit enter, then divide by 6. And r is 0.151. Now another way to do it is take what you've got here, make the right side your y1, make the left side your y2, and see where they intersect. So let's do that on Desmos. Okay, I'm going to type in those equations. So y equals the left side of my equation was 7.425. The right side of my equation, y equals 3e. You can literally use the e on the keyboard. I need to raise it to the power of 6, and you can even type in r. It will still plot that line. Tap where these two intersect, and there's my 0.151. All right, last question for today and for the content for 2.5 is example 6. Zebra mussels are an invasive fingernail-sized mollusk that are infesting some of the freshwater lakes in North America, just in case you needed to know that. Their population increases on average at a rate of 5% per day. Let 700 be the amount of zebra mussels in a certain lake at time where d equals 0 days. Which of the following function, G, models the amount of zebra mussels after t weeks? So first of all, some initial information that's hopefully noticeable. $700 is our initial amount, and it is the same for each of these, okay? And it grows at a rate of increases, first of all, which means it's going to get bigger. So if there was like a 0.95, I'd know to rule that out. Grows at a rate of 5%. So all of the bases are also 1.05. Again, if those were different, I could rule some out. Now it says that it grows, but the rate that it gives you is per day, which means our time is in days. So if it just set it up initially, it'd be that 700, 1 plus 0.05, so 105, t, where t is the days. Now what's weird about this one is that it says, what's the amount of mussels after t weeks? So it doesn't want it in terms of days, it wants it in terms of weeks. So if I just look at what's left, first of all, this is one on the inside and one on the outside, one on the inside and one on the outside. They literally cancel each other out, so we know it's not those. So now the question is, am I dividing by 7 or am I multiplying by 7? Well, if I'm going from days to weeks and I have a rate per day and I want to know what that rate would be per week, I'm going to multiply that rate by 7 because there are 7 times that rate of a daily rate in 1 week. So B is the correct answer here. All right, that wraps up the notes for today. Please make sure you submit to the Canvas assignment and use the remaining time to work on the 2.5 homework. Have a great day, guys.